So, if I could have your attention. This morning when I talked about CSAIL, I said a couple of things about it. One of the things I said was that there are 4 groupings within the lab, and one of those 4 groupings is theory. We have a very large theory group with a large number of faculty. And in some ways, theory is the hardest of the 4 groups to get research funding for. In most of the sort of work we do, we put in proposals and we say we're going to work on this problem and we're going to solve it, and then we're going to work on this problem, we're going to solve it. And we have a sort of linear chain of how we're going to go about doing something. But in theory, the theory guys sort of say, well, we're going to think about this area, and we might prove some theorems, but we might not, because if they knew what they were going to do exactly, they would have already done the work. So it's very hard for them to say exactly what they're going to do in the future, and it's very much exploratory-based research, even if it's in the cryptography area or in the high-dimensional geometry area, which has some applications. Exactly what they're going to do is hard to say ahead of time. On the other hand, out of the theory group has come a lot of spin-off companies, some of which have done rather well. RSA Security is one that you've probably heard of from Rivest and his colleagues with the original encryption algorithms. More recent ones, you'll see some of them at the booth this afternoon in this room. This is, by the way, is the room where we're going to have the spin-off companies, Peppercoin. And another one of those companies is Akamai. And Akamai was founded by Professor Tom Leighton. And this brings me to the second thing that I mentioned this morning, that CSAIL is an interdisciplinary lab with faculty from many different departments. Tom is in the mathematics department here at MIT. He received his PhD in 1981 from the mathematics department, is a faculty member in the mathematics department. And in the theory group, a large number, about half the faculty are actually from the math department and half are from the computer science department. So it really is a group that spans departments and even schools, engineering and science here at MIT. So Tom has been on the faculty since 1981. He, a few years back, he started Akamai, and many of you probably know a lot of the Akamai story, but we're going to hear it firsthand from Tom today. Tom, welcome.
Thank you. Thanks very much. If you have questions during the talk, stand up or raise your hand or just shout out. Be happy to try and address those. And then maybe we'll have time at the end for some final questions. I'm going to talk about the history of Akamai, focusing on the early days. How we started doing academic research at the then Lab for Computer Science, what the problem area was and how we got going, and then how we took it, what caused us to take it from the lab into a company. What were the mechanisms there that were successful? And then I'll just say just a little bit about the crazy times of the bubble bursting, and then going forward from there. So we're going to start with the academic research. None of the people who were involved in Akamai at the beginning ever had any idea they were going to start a company of any kind. This was purely a research project that was motivated by some of the problems with the web. The web at a high level is an amazing structure. It's revolutionized the way we communicate and do business. And it's very simple. You have people that want to get access to content, the end users at home or in the business or at a university, and people that have content that those people want to get access to, and they get the access through the internet. Now, if you look under the covers, things get a little bit more complicated. In particular, the path that the bits take from an origin server or a website to the end user can be long and tortured through the internet. You will typically go through many ISPs or network providers on the path from the origin to the destination. And sometimes things can go wrong during that path. And one of the main problems is at the origin infrastructure, that you have a bottleneck right at the very start, which we'll talk a little bit about. And also at the peering points, either public peering points or private peering points where the bits go from one network to another, you can get into trouble. They can be lost or misdirected or stolen and not arrive at the end destination. And it was the foresight with these problems that led Tim Berners-Lee to walk down the hall at LCS and come talk to my group, which is the algorithms group at LCS. And that's one of the great things about LCS is it's a multidisciplinary environment. Today's CSAIL is a multidisciplinary environment. You have theoreticians from the math department of all places sitting more or less side by side with leading practitioners and people who've made major advances like Tim in founding the web. And Tim knew the web was going to get into trouble even back in '95, particularly with origin infrastructure problems, that if you have a lot of people that want to get to a particular website at one time, that was going to be a problem. And he said, hey, you guys work on algorithms and networks for very big problems, and you do this theory stuff. Maybe there's something you guys can think of here that would be helpful. And that happened back in '95, and that's what got us started. And let me say a little bit about those two problems, the first being the centralization bottleneck, which is still an issue today. The basic idea is simple. A centralized website creates an inherent bottleneck and a great target for attackers. And we've seen this with many key websites over the last several years, from the White House to Microsoft to SCO, that it's a nice target. It's inherently not scalable. As the usage of the net grows and the number of bits you sync through broadband connection grows, it puts a lot of burden on a single origin infrastructure. The web is a good news, bad news story. The good news is it's unprecedented in its ability to support communication. Anybody can put up a web page without a license from the FCC or without having to buy a radio station, and hundreds of millions of people can access that information. It's really remarkable. The bad news is that hundreds of millions of people might actually try to access that information, and they might try to do it at once. And the first famous example of this was the Victoria's Secret fashion show that was advertised in the '99 Super Bowl. And probably a lot of you remember that. They had these models walking down the runway in lingerie in the Super Bowl ad. And they say, if you want to see the whole show, come Tuesday night at 9 o'clock to our website. Tuesday night at 9 o'clock in 10 seconds, that site was toast, along with most of the internet in the surrounding area for the Victoria's Secret website. And that's when people really started catching on. There were several more examples where there was hot content and you couldn't support all the traffic, the people who wanted to get there. And if you do try to support it, you sort of have to guess how big that crowd's going to be. All the e-commerce providers have to guess this Christmas how many people are coming. How big do I build my infrastructure? For the tax guys, it's on April 15th, how big to build the infrastructure for the one day. For the folks that, online commerce for flowers or for Mother's Day, there's big dates where you put all this provisioning in, and if you guessed right, you overspent for the rest of the year. If you guessed wrong, you overspent and you died. And it's a problem. And this is leading to the whole notion of on-demand computing that you see IBM and a lot of the other big companies now putting a major marketing investment in. What's less well understood are the problems in the inherent infrastructure of the internet. So after Tim came to us and we started looking into the problem, we realized there's even deeper, more fundamental issues than just the centralized notion of distributing content. And the first is that people have a notion that the internet has a lot of unlit fiber. There's a ton of capacity. And to some extent that's true. There's big trunks from New York to Los Angeles, some of which aren't even lit today. So there's capacity there. But the problem is not in the trunk fiber. The problem is in the routers that connect these big pipes, at the peering relationships between the various ISPs. So you can get all the bits you want from LA to New York on MCI. You try to hand off those bits from MCI to Sprint to New York or to a lesser known ISP that's handing off to an end user, and now you got a problem. And this goes back not to a technology problem. We can build big routers. There's companies that are really good at doing that. But it comes to an economic business problem. The networks have not figured out how to charge each other for taking each other's traffic and providing transit for that traffic across the country or across the world. And so the best defense is to limit how much of the other guy's traffic you put on your backbone. And you do that at the peering point. And that, if you make that small, that limits it right there. They can't get any more traffic through. This causes congestion on the internet. And the congestion is not typically so much in the big backbone pipes. It's at these peering relationships. And when the router gets swamped, it drops the packets on the floor. Now, that's compounded by the fact that the algorithms that route the packets ignore congestion. The algorithm decides the path your packet takes to go from source to destination is called BGP, Border Gateway Protocol, and that navigates between all the ISPs and picks the path your packet takes. It tries to find the shortest path, roughly in terms of how many routers does it go through. But it doesn't have any way to differentiate between a router that has a ton of capacity and a router that is dying and dropping packets on the floor. And it just keeps sending packets along the same path, irrespective of whether or not the packets are getting through. So that's a fundamental problem, that you don't adapt to problems on the internet. It actually gets worse than that when you go one level deeper and you look at the data that's supplied to BGP to find the shortest path. One would think that you'd get the data that tells you, okay, what's the distance between this point and this point on a backbone, and you'd send that data up into a shortest path algorithm, which we've known how to solve for 40 plus years, and you'd get the answer. That's not what happens. Because of these economic problems between the ISPs, it's the data that it supplies to the whole internet. For example, if a network does not want somebody else using its backbone link between New York and Los Angeles, which they're not getting paid for quite possibly, they will say that the distance there is 20 instead of the true distance, which is 3. Now, when BGP computes shortest paths, when it sees the 20 there, it tries to find an alternate path that's less. So this is how networks influence traffic to go elsewhere. So they're not used for transit when they're not getting paid. Now, everybody is playing this game. And so what happens is the data fed into BGP is in a lot of ways meaningless. So you're finding a shortest path based on bogus data. So the path is not the shortest path. And there's, a great example. You do trace routes. Just, trace route to someplace and see the path it takes. And usually you can see it. That can't be the shortest path on the internet. And there was a great example one day where we trace routed from our building at Akamai, which, you can walk to in 5 minutes from here, to MIT. And it went through Israel. Okay? Now, BGP is doing the right thing. It is finding the shortest path based on the data it's given. And this only way this could happen to go through Israel is all the data is garbage that it's getting. Okay, now, once you have human beings monkeying with the input data, all hell can break loose. Okay, so a great example of this was when level 3, the human being accidentally put in minus infinite, the equivalent of minus infinite cost or distance to go through its backbone. Now, when you do a shortest path computation and there's some edge that has minus infinite length, any path using that edge has minus infinite length. So immediately in the internet, all the packets raced for level 3. Every path had to go through level 3, basically. Well, level 3's peering points are small to protect themselves from too many packets from coming in. Immediately they're congested. BGP doesn't adapt. All the packets fall on the floor. So the internet ground to a halt for about an hour before they figured out what the hell went wrong, and they corrected the information and propagated it. Now, the next day, you look at the paper, and it said, oh, some tractor cut a fiber somewhere, and that caused an internet outage, okay? Because they don't want to tell you the game that's being played. There's not enough tractors in the world to cause all the problems that we've seen on the internet. It actually gets worse than this. The routing algorithms are subject to entire loss of routes and intentional theft of routes. Now, most of you would know this through the notion of black holing. Accidentally, some other guy at some ISP said that he owned your IP address. And he typed that into his router, and that got propagated. And so all of a sudden, all the traffic destined for you doesn't come to you anymore. It goes to that other ISP where some guy made a mistake, typed in the wrong thing. And then that ISP doesn't own that IP address, so it just forgets about it and drops the packets on the floor. And this happens all the time. It's a big economic impact to people that are running e-commerce sites. We had one large hotel chain customer had this happen for 5 hours. Comcast accidentally stole their IP address on the internet. Nobody could get to that website for 5 hours. It cost them millions of dollars. And they're still in legal fights over who has responsibility. But that's just the accidental misuse. Spammers do this to inject spam and blame the innocent bystander. Okay, they will steal somebody's IP space because nobody's really checking about who owns the IP space. And the way you do this is very simple. You get a router or a T1, and you just say, I own these IP addresses. and you communicate that to the router at the other end. And it just spreads that information through the internet. In fact, the bad guy can spread it as, he can actually control the spread. He can go all the way or a little way. Once he has the IP space, dumps on the spam, it goes out, then he goes away. He gets off the net. Now when you go to investigate who sent all that spam, you find the guy who owns the IP address, who has no clue what happened. Okay? It gets worse than that in terms of e-commerce. Like, say you do banking on the internet. I don't know, maybe you have a fleet account here in Boston and you have a password. You have your login name and your password. I can steal that very easily. Many different ways. One of them is because BGP doesn't authenticate ownership of IP addresses. So the way I can steal your password is I go to your ISP and I send a message to your ISP saying that I own the IP address of the bank. And I limit the spread of that information so it only goes to a particular ISP. And that ISP, they don't look at it, they don't check. They say, okay. So immediately that ISP sends me all the traffic for the bank. Comes to me. So meanwhile, I've downloaded the login page from the bank. I just download that. You come to me to log in to do your banking transaction. I show you the login page. Okay? You type in your login identity and your password. And then you get redirected to the site and, oh, you have to log in again because there was some problem. Please log in again. Okay? You don't know that anything unusual happened. Okay? The bank certainly doesn't know. They just lost 3% of their traffic, but that's noise. They're not going to know. And I just collected all the passwords for a particular ISP. And that's one of about 5 ways I can do it on the internet today. And people don't have a clue, okay, that don't have a good understanding of how vulnerable things are on the internet today. So these are some of the deeper problems that aren't as well understood in the internet infrastructure today. And this is where we got started with Akamai. Now, one of the issues we faced early on, and still face today, is people have the impression, well, it's going to get better. That there's consolidation. That there's going to be 2 or 3 tier 1 networks that are going to own everything. They're going to get together and they're going to work it out. And really the reverse is happening. When we started Akamai, there were 7,000 networks that made up the internet. And today there's 15,000. There's been a lot of high-profile bankruptcies, but not a lot of consolidation, even among the tier 1s. The other misconception is the tier 1s run the show. And that's not true. Pretty much any tier 1 will claim a 40% market share. All 24 of them. And you can sort of know that's not right. That's not hard to check that. But in fact, all the tier 1s put together control less than 25% of the bits that are handed to end users. Most of the bits are handed off to end users by companies you've never heard of. And the curve, if you want to get a 95% coverage, you're into probably close to 10,000 ISPs in terms of handing the bits off to end users today. So it really is a very distributed infrastructure that doesn't really have any particular control over it.
How many of those ISPs are in the US?
What's that?
How many of those ISPs are in the US?
I don't know the exact figure, but there's dramatic growth in traffic now overseas. Today China is the fastest growing sink of bits on the internet. And Brazil, and also a very large growing consumer of bits on the internet today. So it's becoming much more international. If you look at our traffic graphs, they're getting almost flat now. Whereas several years ago at nighttime there's a lot less traffic in the US. So the internet is becoming very international. Okay, so what are the implications? What creates a business case potentially for a company or something that makes it interesting as a research subject? Well, these problems make downloads be slow. Applications are very slow. They're unreliable. The infrastructure is inherently not scalable, the architecture of the internet. And Tim recognized this way back in '95, 4 years before Victoria's Secret's fashion show. He said this is going to be an issue. It's insecure and just much more than people really realize. It's expensive. If you want to provision an e-commerce site or something that's going to do business or protect your brand on the internet, you've got to spend a lot of money building up your centralized infrastructure. Another misconception is that broadband solves the problem. Okay, now actually broadband makes the problem worse. Because now you have people who are syncing bits, they expect to sync bits at 20 times the rate they were before. Right? Instead of 50 kilobits a second, they want to go to a megabit a second. That puts more load on the central infrastructure and on the peering relationships. So it creates more of a problem. It solves the last mile problem, but not the internal infrastructure of the internet. Okay, so what was the idea at a high level behind what Akamai was going to do? And back then, the research. All right, so Tim comes in and says, we've got this problem. Okay, well, what do we think we might try to do to deal with that? And the idea at a high level is very simple. Use a distributed infrastructure and architecture instead of a centralized infrastructure and architecture. And that's an easy idea for us because we did distributed algorithms on networks for a living. That's what we like to do. So even if it wasn't a good answer, that's what we were going to do, okay? Because that's sort of what we did. We'd write a paper on it, and that would be the end of it if it weren't useful. So the idea is to take a zillion servers, place them all around the world across the last mile from the end users. Place these servers in those 15,000 ISPs. And instead of serving the content from across the world or across the country, get it into these servers here and serve it locally. And if every once in a while you needed to go back and get something from the origin, well, you'd build some kind of architecture to do that. But now all the interaction is local. That's the high-level idea. And the idea is that this would be better because it would be faster. Everything's local, so it's going to be faster. It's going to be more reliable because you've got a distributed infrastructure. If some of the servers died, who cares? You've got 10,000 more. It would be scalable. You wouldn't have to worry about scaling up that central infrastructure because you've already built this large platform and an individual could use more of it on demand. It would be secure because you couldn't even get, the end users couldn't get to an origin infrastructure anymore. They'd only have to deal with these servers spread around the world, and they would be beefed up to provide a shield to an origin infrastructure. And it would be cost effective. You could make a pitch to somebody who owns a website saying, don't worry about provisioning. Don't worry about redundant data centers. We'll get it all backed up for you and replicate it in our distributed network. And it's easy to manage. We take care of all that hard stuff using the math, okay, the distributed. Now, well, how do you make that really work? And back then, back in '95, you went out into practice and you said, we're going to build this gigantic distributed network and it's going to serve all the web pages from all the leading websites. And they'd have a great yuck at that, right? That's pretty funny. And there's a reason you guys are in the ivory tower instead of out here in industry. So we spent a lot of time actually doing the theory, figuring out how to make it work. And a lot of our early effort was, how do you coordinate all those servers that live in this unreliable internet? How do you direct an end user who wants Yahoo's web page to the server that's really nearby them, that has Yahoo's web page, it isn't overloaded, and all those kind of things? And you got to do that in real time. You can't, the request doesn't come in when they click the browser and you think for a few minutes to give them the answer. It's got to be ready to go real time. So there's a lot of effort in coordinating that. This is not a problem we thought about in the early days, but as a company, you got to bill for this. The guy who has the website you have to send him a bill to be in business. And actually, we're billing today for 30 billion things a day. You take the phone company's billing problem and multiply by 10 or more, and that's the billing problem we have today. Because we're billing for every single hit, and there's many tens of billions of hits a day. That required a ton of effort in terms of thinking ahead of time to manage that problem. So today we manage that with a team of maybe half a dozen people, for billing, and it required a lot of thought to how do you get a large-scale distributed billing process. Also, there's reporting. Once you take over a customer's website and you're serving from these servers all around the world, they want to see what's happening to their content. And you got to report on that in real time. And that's a huge information gathering problem that is very complicated. How do you make it really work with operations? That you're running this thing. So it's not just the paper anymore. First there's code, which was very scary. And then the code has to work. And you got to maintain it. So a lot of research there. When you're handling content from websites, people change their content all the time in unpredictable ways. And you got to make sure the content is always fresh. So you're never serving anything stale, without having to always go back and get it. Because the whole point is it's in this server local to the end user. Of course, then you have things like streaming, live streaming, and webcasting, where you've got to manage you don't have the content stored there ahead of time. It's coming live from a source, single source that you've got to distribute in a fault-tolerant way through the internet. And multicast won't cut it, because if you cut it, if you break the link somewhere, everybody downstream in that tree is dead. So you got to build something that's fault-tolerant to go through the internet for your streaming. If we're going to have the entire interaction be at a server near the end user, you've got to be able to assemble the page dynamically, because pretty much all the websites today are personalized and dynamic. The content you get depends on where you're located, who you are, what your cookies say about you, and the time of day. So the HTML is assembled dynamically. Most pages are not cacheable today. And finally, you're going to want to have the applications run on this server near the end user, not at the origin infrastructure, which is a whole another level of complication to have the apps running out at the edge server instead of an origin infrastructure. So these were tremendous research challenges which we spent years working on, never thinking about a company, quite happily cranking away, writing our papers and writing theses and so forth. Now, what converted this into practice for Akamai was the 50K competition. This is a competition at MIT run by the Sloan School. It's a student-run business plan competition. And the winning team gets, actually, it's $35,000, I think, not 50. It's 50 total. And they get tremendous involvement among the community at MIT. There's 1 to 200 teams get together to write a business plan for the 50K. And so let me say a little bit about that process, because that's what, in our case, made the tech transfer happen. So it started with Danny Lewin and Pritish Nijawan. Danny was my student over at then LCS, and Pritish Nijawan was his next-door neighbor, and he was in the Sloan School. And Danny wrote a prize-winning master's thesis on how should content be delivered on the internet, addressing a bunch of the research challenges that I just outlined. And one night they were having beer, and they were commiserating about how Danny was never going to have a career and never pay off his student loans. I think he had like $30,000 in student loans. He was married. He had 2 kids in private school, and he was a theoretician. That's like, the worst possible combination. Because, Pritish, he's at the Sloan School. He already had a job lined up, $250,000 a year. He's a happy camper. Poor Danny, he was in computer science, but he was a theoretician, a theoretical computer science, and the job prospects there were much, much less, promising, to the point where he wasn't sure he was ever going to pay off those student loans. Now, Pritish said, hey, Danny, in an effort to cheer him up, there's this thing called the 50K competition. You're doing some cool stuff in your thesis. Write it up into a business plan. You might win, and you might get $50,000. So Danny was all excited. They needed somebody with gray hair, so the 2 of them came and corralled me, and they talked me into it. So we wrote a 3-page business plan and sent it off. It turns out there's an early round of the 50K called the 1K. And they have 10 categories in the 1K. And lo and behold, we won the software category based on our 3-page business plan. Now, it wasn't $1,000 we got. Since there's 10 categories, we got $100. So we went out to have some more beer with $100. Now the 3 of us are having beer. And Pritish, who's involved in the Sloan School, said, hey, guys, this is pretty good. We won the software category here. We got to go with a full round, and we have prospects here. Pritish was a little clued into what was going on out in the real world and in the 50K and so forth. And so we said, okay. And we got together and we wrote a 25-page business plan. And back then we measured the quality of our plan based on its length. We had no idea what really a business plan meant. Now, somehow we made the final 6 out of the 120 or 130 teams they had. And Pritish came and said, guys, this is really big. He's just totally excited. And, Danny and I and the people that had joined us by that time, we were doing this as an academic project. We could learn about how to write a business plan. We went out and got books, how to write a business plan. We started talking to potential customers. Now, back then, we had this crazy idea we were going to sell our technology to ISPs. And so we went out and talked to a couple. And then we got very discouraged because we realized even back then they were about to go broke, and there were fires burning left and right, and there's no way they're going to pay for our stuff. But then we got the idea we would talk to people with websites. We called up CNN. We called up Yahoo. And because we were MIT and not selling them anything, they were happy to talk to us. And they said, well, that's sort of cool stuff. And if you changed it this way, yeah, we might try that out, kind of level. So it got us a little more interested. And then I started to get the impression this might have been big when some business guy from California showed up in my office wanting to join the team. What? So I said, okay. And by now we had like 25 people on the team. And then I knew it was really big when a guy from Harvard Business School came all the way down Mass Ave to join the team. And then I knew we were onto something, and at that point. So the team got up to about 30 people at this point, and it was really getting pretty active. And we wrote a much better business plan. It was 55 pages at that point. And we went into the final 6. And we lost. And not only did we lose, we lost badly. They announced first, second, and third. First was a nonprofit organization. And this is a business plan competition. I am sure we were dead last. They just don't announce 4, 5, and 6 to avoid the embarrassment. And this was a slap in the face. This was a group of people who weren't used to losing and weren't used to being embarrassed. And we were embarrassed when we saw the quality of the other presentations, the other 5 teams. They were good. They knew what they were doing, and we realized we didn't know what the hell we were doing in terms of a business. We could write great papers that very few people would ever read, but when it came to a business, we had a lot to learn. Now, the fact that we lost notwithstanding, the VCs came to us after the 50K. They sort of see what goes on, and they said, guys, look, this is MIT. It's the internet. It's hot. We'll make a company. We'll flip it. 6 months. Everybody goes home happy. Well, we didn't want to do that. And we actually made an active decision not to form a company in the spring of '98. Danny wanted to be a professor, even though he was never going to pay off his student loans. I liked being a professor. The students, by and large, liked what they were doing, and this had been an academic project. So we said, no, we don't want to do that. But we were intrigued, by the idea. And we said, well, if we really felt we could commercialize this and we could be really successful, long-term successful, it's worth doing to get the technology out there and to make a difference. And so what we did is we spent the summer with a program at MIT in the Lab for Computer Science. It was then called Hacker Haven or Hacker Heaven. And this was a program set up in the lab where there's maybe 50 really smart undergrads that love coding. And you take them for the summer and you put them on a project. And we were one of the projects where here we wrote all these great papers. We have these cool algorithms, but we really hadn't written any code. Let's make some prototypes to see how a system would work for content delivery. And a bunch of the students thought that was cool, so they signed up. And meanwhile, one of the folks we called up to see would they ever buy this service from us was Paramount Digital Entertainment. Now, Paramount owns Star Trek. And they said, hey, look, if you guys could do this, we'll let you distribute the Star Trek TV series over the internet. And by the way, here's a bunch of Star Trek paraphernalia. So I got my Captain Kirk tie and my Dr. Spock stuff and all the cool hats. The kids went nuts. They were 24 hours a day, they're writing code. They just, that little tie and the hat with Captain Kirk and Dr. Spock was all it took. So they're cranking away over the summer. And by the end of the summer, we actually had 2 prototypes that showed that, hey, this really can work in code. And we thought some more about the business plan, and we actually had a plan that we started believing in, as opposed to the 55-page plan, where we sort of understood the number of pages in the plan. And so we decided to take the leap, got together at the end of the summer, and we incorporated. And my colleagues at LCS were much happier, especially those that lived next to me, because I had these 30 people involved in my office. And it was a zoo at LCS while people were writing code, and there was this 50K plan, and it was very exciting for us, but disruptive. And once we incorporated and decided we're going to go commercial, then we leave MIT. And we had to get offices outside of MIT, and had to actually pay for it ourselves, negotiate with MIT over the intellectual property, because we'd done this stuff at MIT. MIT owned the rights to it. And so we had to make a relationship whereby MIT took some equity in the company we formed, and then we got the exclusive rights to it, in a process that in the end worked very well. And we had to buy some servers, So instead of just on paper servers, we had real servers. We got a real business person. The original team of 20 people were all MIT folks. In fact, they're mostly MIT undergrads that formed the company. So everybody was involved in the project. We said, look, come on board. You can join the company. Everybody got equity. The only rule we made was that you had to finish your degree. So we let students take a year off, and they had to come back, and we let them keep vesting while they came back to finish their degree, because we didn't want to, screw people up, that way. And fortunately, everybody did go back and eventually get their degrees at MIT. One of the things misconception we had early on was, hey, once we just say we're forming the company, the VCs are going to send checks our way. And it turned out not to be that easy. They would take the check, but actually getting the terms to be what we considered to be reasonable took a long time. In fact, we had to go the angel route to the start. And even the day we were going to close the first round with the VCs, one of the VCs pulled out that day. We had the signed term sheet. We had the handshake. Everything was done. We're going to sign. And we learned the lesson that you don't deal with the junior partner. Because the senior partner decided he was going to teach a lesson to the junior partner and said, this is the kind of deal you don't want to do. And so the day we're going to close, he pulled out. And we were very glad that Battery stayed with us. Battery Ventures was our lead VC with Todd Dagres. And they stayed with us. They closed the deal without the partner, which was hard for them to do. And we didn't get the second partner until months later. Now, eventually, the VC who pulled out did regret the decision. So we finally closed the first round. Months later, we were stretched at that point. We'd spent hundreds of thousands of dollars of our money and our family's money at that point, so we were glad to get that done. I'll go briefly through this, as now we're getting to the stage where outside of MIT. We deployed servers at that time into Exodus data centers. Jonathan Seelig, who joined the team from the Sloan School, got Ellen Hancock, who was CEO of Exodus, to give us 3 free months of bandwidth and colo. A decision she regretted because she spent much of the next several years trying to kill Akamai as a company because she felt it was competitive. Our first internet test, we wanted to actually test to see if we could, if the thing could work. So we did it on Exodus. We said we're going to drive our servers to the max. They said no problem. So we drove them to the max. We took out Exodus, and a bunch of the internet went down when we ran that test. It's the last time we took down the internet from the test of our servers. The first live object was an object on a back page of the Disney website. We got about 1 hit every 5 minutes across the world on that site. And we had a dramatic ramp up in traffic. The first big break, there are actually 2 breaks in the same day, came to us, was March Madness in '99. And we've been trying very hard to get into ESPN, which was a shop that was viewed as a leader in doing things in the internet back then. And we've been trying to get them to test out our process, to show we could be faster and more reliable. March Madness came, ESPN went down. And I remember the day they called us up and said, hey, that test you want us to try, we'd like to try it out. We said, okay, here's how you set up your URLs. So they point to Akamai and we'll deliver them. So they did that in about 15 minutes. And they said, okay, by the way, can you guys take 1,000 hits a second? And we're doing 1 hit a minute on the system, the live system. So we said, sure. And this is where theory helped, because normally when you build a live system, you scale by a factor of 2, another factor of 2, and then you sort of redesign, you do another factor of 2. And the theory had been built to go to millions of hits a second. And it actually worked. And so they went to 1,000 hits a second. They said, OK, this is good. And they put the entire site on us. And all of a sudden, it's 3,000 hits a second. So we scaled up 5 or 6 orders of magnitude within an hour. And made their site faster. And that was a huge break for us as a company. That very night was the night that the Star Wars trailer was going to be released. Now, this was a big event back then. People would love to get the download of the trailer. Now, Steve Jobs had paid for the rights to have the trailer to be exclusively distributed on QuickTime, exclusively on the Apple site, because he was trying to make a dent with QuickTime against Real and Windows Media back then. And we didn't know any of that. But Entertainment Tonight has a website. They came to us and said, look, would you distribute the trailer for us? We said, sure. Entertainment Tonight, it turns out, had a bootleg copy. They weren't supposed to have it. Only Apple was supposed to have it. So the trailer was released at 9 p.m. in the evening. And by 9 p.m. and 30 seconds, Apple was down. All the other bootleg sites were down. And Akamai was cranking out Star Wars trailers just fine. So Steve noticed this. And wasn't so happy, but we got a lot of great press because all of a sudden the web noticed that there's this thing called Akamai, and they're delivering and nobody else was. Shortly thereafter, on April 1st, we're cranking away in our offices, writing code and stuff like that. And our president then, Paul Sagan, comes out of his office and said, okay, which one of you bozos is pretending to be Steve Jobs trying to buy the company? And we're looking around. And he goes, oh, no. And he runs back into his office to call back Steve, because he hung up on him. And it really was Steve. He thought it was April Fool's joke, because we always do these April Fool's jokes. But it was a real thing. Now, in the end, we did not sell the company to Apple, but Apple became our first strategic investor. And to this date, we have a great relationship with Apple, and we handle iTunes, their e-commerce site, and pretty much everything they do. All right, let me go quickly through the bubble mania. Very quickly in '99, things exploded. We added on a tremendous executive team. We took on Cisco and Microsoft as strategic investors. We went public very quickly on October 28, 1999. Turned out my birthday was the night we priced the IPO. Before you knew it, we had a $35 billion market cap on about $5 million of revenue. And that was excessive even for the bubble. That was out there. We had bizarre problems. We had these 18-year-old kids who were multi-millionaires, and how do you deal with that? Help them to adjust to that. Of course, by the time we figured that out, we had the reverse problem. How do we help them adjust to the reverse problem? So AOL bought Time Warner. We bought a bunch of companies. We had massive expansion, no budgeting. You just bought. We grew to 1,400 employees overnight, and then the bubble burst. And we had just the reverse process. We downsized to 500 employees. It was very painful. We had to revamp our entire customer base. Almost all of our customers went broke. It was a nightmare. So we had to get on stable customers, enterprises, and the government onto the system. We had massive pricing pressure. The cost of bandwidth dropped by a factor of 100 over a several-year period. 100. It's unbelievable. And that put a lot of pressure on us because we were compared sometimes to bandwidth. We had to put in a budget into the company, focus on cost controls and profitability. We had hundreds of millions of dollars of real estate we were never going to use and was underwater by a factor of 5. Some of it which had been purchased by MIT in the interim, which we eventually worked out a deal on. So we had to get rid of all the real estate, we had to move, and we had to refinance our debt. And our market cap went from 35 billion to 75 million. It's a remarkable decline. Somehow we survived. And I should mention the worst, far worse thing is our co-founder, Danny Lewin, was killed on American Flight 11. He was on the flight that crashed in the World Trade Center. Absolutely devastating. He was the heart and soul of the company, and it was horrible. A tremendous individual was killed. So it was very, very tough during those years. Fortunately, we survived. Today, we're basically a profitable company. We will be, I think we're projecting to the street's projecting 20 or 25 cents a share this year in 2004. We're generating substantial free cash flow today. Revenues are growing substantially. We are still, to this day, have a very heavy focus on R&D. We still have a ton of MIT and students from other universities and professionals from other companies working at Akamai in R&D today. And the market cap has recovered from its lows. You still need a double logarithmic plot to track our stock over time. It's been pretty wild. Just a snapshot of where we are today, and then I'll finish up. We actually have 15,000 servers deployed all around the world today. They're in 2,400 different locations, in 1,100 networks. So we haven't got all 15,000 yet, but we're in 1,100. It's a unique concept to this day in the internet to be in all these different networks. On a daily basis, we're over 40 gigabits a second. Last week, we had a peak of about 75 gigabits a second. Combination of news events on an average basis. We have over 1,100 customers. A lot of the biggest and best-known sites on the web today are Akamai customers. They use our service to be faster and more reliable. This is a typical sales tool. It shows the performance of the website without Akamai, and that's a time plot of how long it takes to download a page or an object. So without Akamai, it takes a lot of time up here, and with Akamai, it takes a lot less time. And then the rest of that pitch is speed matters on the internet. And we've just done some important case studies for us as a business. With a large hotel customer, they switched to Akamai. We made their site faster, and they did a study that showed that produced $30 million more a year of revenue for them by increasing the conversion rate. If your website is faster, you get a higher conversion rate. A very large e-commerce provider, which I think we're going to be able to announce hopefully in the next couple of weeks, the improved reliability and a substantial decrease in their exit rates has produced a quote of $50 million a year in improved revenue. And then even the smaller e-commerce sites, actually those we can get a bigger improvement in conversion rate because we make them that much faster, getting a substantial improvement in their profitability by making the website be faster, more reliable. And that was the original business plan, way back when, coming out of MIT. Long-range vision, where are we headed? Today we're focused on the internet. We're moving now into the extranet. Longer term, we'll go into the intranet. Today we do internet work for the government and a very few enterprises. And we want to distribute. We do that content delivery today. We do page assembly today. We're starting with business logic, running the apps on our platform, and then evolving into web services, and eventually the databases. And combining all these into an on-demand global computing utility. And the marketing is similar to IBM, and they're our largest reseller. So it's a very synergistic relationship. Okay, let me stop for any questions. Yes?
Tom, have you thought about pervasive computing and how you might play in that with wireless?
Right. What's that? The question is how we play in pervasive computing and in the wireless space and so forth. We're working very closely with some of the wireless providers, in terms of providing the bits to them in an efficient way. Today, we are deployed into their networks as far as the IP goes. As long as it's IP enabled, you'll find our servers there. We will sense what device you have. Is it a low bandwidth device or a high bandwidth device, and automatically give you the right kind of content. So you get the richer content if you're a high bandwidth device. You get the text version if you're a low bandwidth device. So it's automatically getting the right version of the page to you based on your bandwidth. In terms of grid computing and computing everywhere, we're probably the largest example of a grid computer today. The difference is we own the servers. It's not on servers in your home. And so it's a more controlled environment, which it allows us to have better performance, a better security than a situation where we don't own the servers and they're in people's homes, which is much less reliable. Yeah?
Tom, you had a program for small educational institutions, colleges and junior colleges, that you would put the Akamai servers in their local network if they would allow you to run that part while they got all sorts of other benefits. How did that survive the bubble?
It worked great. So this is a program where we will place our servers into ISPs that have the end users. And one class of ISPs is the university networks. So we have servers in MIT's network. We have servers in 200 other campuses around the world. And that enables us to get free bandwidth and colo. So it saves us on cost. It enables us to get better performance for our end users because we're close to the end users in the university systems. The universities do it because it saves them money. They don't have to pay the upstream provider to keep downloading the content all the time. And it makes the performance better on their networks because the content is sitting there that they need. And that program has worked very well. And that's the kind of thing that helped us through the bubble because it helped us on our cost side and maintained our performance advantage. Yeah. Yeah.
How did you come up with the name Akamai?
Danny had a friend who was in marketing, and we said, we're looking for a name. In fact, our early name was Cache when we were in the 50K competition. And then we realized caching was going to die as an industry and decided we better get a different name. And he said, Hawaiian names will be in. So we got a Hawaiian English dictionary, put 50 Hawaiian words on the board, and Akamai means clever, intelligent, and cool in Hawaiian. So in Hawaii, you say very Akamai as a compliment. And we did a search, which came up clean, so we took the name. Then a year later, we realized the search hadn't been done right, and there was a company called Akamai.net in Hawaii, and we had to buy them to preserve the name. Yeah?
Your distribution model seems very much like what we would call in the logistics space a logistics distribution model. It's basically an intermodal model where you have points of excellence for distribution on a localized level. Was any of that thinking ever involved when you started pulling these ideas together?
Not from that space, because we didn't know anything about that space. And I don't even recognize the terms today. But the same ideas that are useful in that space, I'm sure, are the ideas that made this appeal to us. Yeah?
Just some idea of your pricing model. Essentially, how small a company can benefit from your services?
Anybody who cares about their web presence. So, there's companies that have no traffic on their website at all, tiny traffic, but they care about their brand, and they want it to be up and be reliable. And so then they would be an Akamai customer. If you don't really care about your web presence and you have tiny local traffic, well, then you probably wouldn't be an Akamai customer. I think our smallest customers would pay $1,000 a month for the very smallest to start. So that would be a barrier right there to a lot of companies, I would guess. Yeah?
At the beginning of your talk, you were talking about security issues of BGP, but I kind of missed any comments on the scope of your solution you're providing.
Right. Okay, so we actually have an offering today that we call BGP Watch. Because we're in these 1,100 networks, we can get all the BGP feeds from those networks. And so we can actually flag if somebody starts advertising an IP address for one of our customers. And we can tell our customer, hey, all of a sudden, somebody just took your IP space. You better go check it out. Because we can look for changes that way. And we do this for several high-profile government customers. And now in the financial vertical, obviously some of those customers care very much if somebody's taking their IP address. And this is something they can't get any other way. You can't get this from MCI because MCI may not even see it. And it's only because we're in this large footprint that we can actually see what's happening in the routing infrastructure at that level. Yeah?
You learned any new surprising things from your operations data that would challenge the underlying theory or stimulate new theoretical work?
Nothing that would challenge the underlying theory. There are interesting things we learned. For example, the internet does not satisfy the triangle inequality. The triangle inequality says that if I take two sides of a triangle, it's longer than taking the direct path. That's not true on the internet. And that's, so for example, the direct path given by BGP, the only path, often is bad. And there are better paths if only the internet would give them to you. And so one of the things we did in response to that was build an overlay network on top of the internet so that when the direct path is not working, what we'll do is encapsulate the packets at the source, send them to an intermediate Akamai server across BGP, and then unwrap them and send them to the destination, thereby taking a longer path around the triangle, which in some cases is a lot faster. In fact, today, if you're going between the US and Asia, the direct path is usually a bad path compared to what you can get. Yeah?
Why do you think that some of the companies like Akamai that focus on route optimization haven't been as successful?
Well, it's a brutal economic climate out there. I think 99-point-something% of the companies went broke. And Akamai had some great ideas and great technology. They eventually got bought out by Internap. Internap is selling that kind of technology today. I think ultimately it will be successful, but it's a brutal economic climate today, and it's extremely hard to get profitable. And today you got to get profitable, or you're gone. Yeah. Oh, sorry. Okay.
Can you say a little bit about the choice between a service-based business and a product-based business? Was it an accident of the customers that you happened to be able to get at the time, or was this more of a conscious decision?
Right. So with the customer base, it had to be a server-based. Once we switched to the content provider as the customer, it had to be service-based. You can't, because we have to have the server spread all around the world. Somebody's got to run and operate that. And so the only way really to sell that is as a service. When we go behind the firewall, now you're sort of building a mini Akamai behind the firewall. You can think of operating that as a product. And we have thought about that. In the cases where we're doing that today, we're actually selling it as a service. So we will come manage it behind your firewall, or in the government space, we will come and manage it. And that's because it's better for us to do it that way. This is the way we're set up as a company. There are competing vendors. You know, Cisco will sell you products that say, you can be an Akamai, just buy my hardware. And they've had limited success at doing that.
Okay, thanks very much, Tom. That was great. Again at 2 p.m., which is 11 minutes from now, for healthcare and biology. See you over there.